Good morning, everyone, or afternoon, depending when you're watching this video. I just wanted to go through this real quick and kind of give you the key for this in case you missed any of it. So you're going to open up the Nearpod. I know I'm a big fan of Nearpods, but I wanted to be able to draw and label some things, so that really leads me to the Nearpod or Cami. And at this point, I'm not learning Cami. So, as typical with Nearpod, I get to watch this beautiful picture of fluffy clouds on a snowy winter day with vanilla ice cream and a polar bear. Everyone see it? Of course not. It's a white screen. If you get this white screen, just refresh. And this would be the reason why I got off of Nearpod in the first place. All right, so log in with Google. Use your account, not mine. You can't get my account. Hey, that's me. All right, so what we did is I was kind of using this as a conclusion to talk about the catapults. We used to do a much larger project with this, but I wanted to kind of at least include something to your hands-on opportunity with. So we are going to look at a catapult. We're talking about the materials that and kind of the processes that are involved in a catapult and how they relate to what we've been talking about so far in my class. So, good introduction to the catapult. Okay, I'm not sure why it's not making noise. Oh, it's not playing.
Hello, and welcome to the History of the Catapult in 2 minutes or less by me, Aaron Lightfoot. The earliest recorded versions of catapults date back to the ancient Greeks. The Greeks gave us important people in history like these dudes and this dude. But in 399 BC, Diodorus Siculus, the historian, recorded one of these early catapults. Obviously, this one looks quite a bit different than what you may think of as a catapult, but it had the same basic function: throw things. These early catapults looked similar to large crossbows and had pulleys to pull the projectiles back. Let's fast forward a couple years to the Romans. In 350 BC, during the reign of Philip II, there were records of a different type of catapult being developed. This type of catapult, more specifically a torsion catapult, had an arm connected to the base.
This is the kind that we built.
This is starting to look
called a mangonel.
Catapults were a fairly prominent military necessity up until about the medieval times, where they were largely replaced by this thing, a trebuchet, which had the same general function as a catapult, throwing things. Hundreds of years later, though, man was still using the concepts of early catapults in their military technology. In the days of tanks and artillery, our little catapult was still being used to chuck grenades across no man's land. Eventually, they were pretty much 100% replaced by mortars and artillery. Today, it seems safe to say, as far as modern use goes, rest in peace, catapult, you served us well.
Alright, so that's a little background on the catapult. You won't be able to skip it, you have to watch the whole thing. It's only 2 minutes. I'm going to go ahead and change all mine because I want to make sure I start from the beginning. On this one, what we're going to do is label the basic catapult and the parts. You don't have to draw arrows, you can just label it. So we're going to go through all the parts. The spoon part where you put the projectile was the base. We call that the basket. I apologize, the basket. So the 4 terms we have to identify are, we have to submit this first. Basket, the arm, the base, and the fulcrum. So the basket is the part that holds the projectile. In this case, it was our spoon. The stem of the spoon is our arm. The pivot point is called the fulcrum. So in our case, it's where the rubber band and the ties the string to the string. Ties the spoon to the popsicle stick. That is the fulcrum. Fulcrum. I apologize if you couldn't see that. And then in the main part, the structural part that holds it all kind of together, is that base. Okay, so we have our basket, we have our arm, we have our fulcrum, and we have our base. Submit and then move on. So what I did was I uploaded a picture. If you did not build the catapult, copy and paste the picture in. If you can't get this to work, please just ignore this part. I just wanted to see kind of what you had built, but if you can't get this part to work, I'm not going to grade that part. I just wanted to see some examples, but there'll be another chance for as well. So if you can't upload it to there, don't worry about it. I'm not going to be grading that. I will be grading this though. So let's take this from the beginning.
Originally, we were going to hit all the same target, but we found out that our catapults launch the ball differently with slightly different distances, as you can see from the video. So the catapult will be hitting their own targets. But first, this is how each catapult works.
So this is kind of the catapult you built in a different format. Okay, so this is similar to the catapult that you may have created. In this example, the potential energy is stored in the actual bungee cords. By stretching them out, you build up what's called elastic potential energy. When you let them go, that elastic potential energy will swing back down. That will propel your basket forward. So it's the bungee cords that will provide the potential energy in this case. No!
It's arranged in such a way that's kind of very difficult to explain. This rope gives
this is called a torsion.
Tension to make it actually
the twist
swing.
of the rope is what actually makes it spin, so it wants to turn with the rope.
This is very unbalanced.
And this is the trebuchet.
This is the weight, and when that goes down, this arm swings.
Okay. So as the arm of the catapult comes forward, we can see that the projectile was traveling in this path, and it continues to travel in that straight path at a constant speed. The tendency that for an object to resist a change in its motion is its inertia. Inertia.
Rope with the sack here. This is where you put your projectile, like this. You put it right here, and then you let go, and then.
Okay, so in this type of trebuchet, what happens is you watched the weight. You had a bunch of weights here, and they got pulled down. This type of catapult uses the pull on the counterweights to move the arm and gives the energy to the projectile. Where do the counterweights get their energy? Basically, it's asking what is pulling them down. Well, it pulls everything down. That is gravity.
I've added a spring here just for just extra force to bring it down.
So he's using some elastic potential energy as well.
The trebuchet, and you can see the measurements that are listed on there. The ideal ratio from the short arm to the long arm is 1:3. Also, this hook at the back of the arm is very important to the operation of the trebuchet because you need a very specific angle, and the only way to determine the best angle is from trial and error. All the tension is right here in these bungee cords that go around. This is an extra long arm so that right here where the cup is, it goes really fast.
Okay, according to Newton's second law, force equal to mass times acceleration, or F equals m times a. So if I wanted to propel an object with a greater mass, what would I have to do? If I want a larger mass to move, I'm going to have to apply a greater force to it, so we need to increase the force on the object.
You can adjust the angle here. Pull it up. Stick a few wooden rods in.
Sorry about the music volume.
And you can adjust the angle.
Alright, so there's a bunch of math that we're talking about the actual formulas. You don't need that. We're just talking about the energy in the system. Okay, so moving on to the next one. We have a fill in the blank. So again, catapults are devices that use potential energy to launch objects in a specific direction. They use a lever and a fulcrum. The lever arm, the lever is the pivot arm. In our popsicle thing, the lever is kind of this, the popsicle, not popsicle, it's the spoon stem. That is kind of our lever. The fulcrum is a pivot point. For us, the fulcrum is that point where the rubber band holds that together. That's where this whole thing pivots. Actually, it's bending. Wow, it's not good. Now, potential energy is stored energy. So when you pull that arm back, you store potential energy. Where did it come from? You gave it to it. When you release it, it starts to move, which means that potential energy changes into kinetic energy. Now, the projectile in the basket is going to move forward until the object stops. But once the spoon stops, that projectile is still going to keep going on the same path. It has a tendency to continue on the path it was going. The tendency for a projectile to keep moving in the direction it is moving is called its inertia. So once again, if you missed this, catapults are devices that use potential energy to launch objects in a specific direction. All catapults use a lever and a fulcrum. The lever is the pivot arm. The fulcrum is where the arm pivots. It's like that access point. So where my hands meet would be the fulcrum. If you think about a seesaw or a teeter-totter, okay, so if a teeter-totter is going back and forth like this, the point where they both rest, where they pivot, that is the fulcrum. We don't do small, simple machines in physics. I wish we had time for it. If we maybe at the end of the year, I'd love to do it. Potential energy is stored when the arm is pulled back. When it's released, the potential energy changes to kinetic energy or energy of motion. As the basket stops, the projectile keeps moving because of its inertia. Okay, and when you're done, I'll tell you what you got. I've included a simulation here, and I want you to be able to play around with it. There's some good things about it and some bad things about it. It does allow you to change the masses and the velocities and the angles. So let me move myself here. All right, so I'll be able to reset. So if I change this, let's go 45-degree angle, and let's go 15 meters per second, and let's launch a golf ball, an object with very little mass of like 1.05 of a kilogram. Not much. What's that, 50 grams? So if I launch it, okay, you see the projectile path. Now I would have the total, the vectors on. I'll launch it again. Because the vectors, and I put it in slow. So what the vectors show is right now I have gravity pulling it down. I have the inertia of the object, the applied force still pushing it forward. And you can see how the trajectory changes as those change. Oh, that's slow motion. So we see how the trajectory changes, the combination. Now, here's the thing that's different about this. I don't want that. If I use, let's say, a car, okay, so I'm not going to change the angle, not going to change the initial speed, but I have changed the mass dramatically. If I'm using the same initial speed and the same force, when I launch a car, it should not go nearly as far. But let's launch that car. And what we notice is that the car does go almost the exact distance as a golf ball. So this is where the simulation kind of fails, because we can imagine that if we had the same amount of force, it would launch a golf ball much farther than it would launch a car. Why? Remember, force equals mass times acceleration. So if I have the same amount of force applied, an object with very little mass, like a golf ball, cannot be accelerated as much as a car, or it can be accelerated way more than an object with a huge mass, like a car. Now, if you increase air resistance, okay, so if you want to add some air resistance, you can see how this impacts your flight. Doesn't impact it much, but we'll see it'll fall just a little bit short of the other car. That's again because air is pushing against it. Let me see if I see it. I do see. I can see a new air resistance should be giving me an arrow back. It's not. But we see how it's just a little bit shorter when you add air resistance because that's going to be pushing against it. Nothing to do with this. I just wanted you to have a chance to play around with it, explore different angles and things. You can measure it. You can try different things. Your goal is to try and hit the target if you want. But I just wanted to have you give a chance to play around with it. All right, let me move myself down here now. Come on. Thank you. All right, a catapult is a device that has been used for many years. And what a catapult does is it changes potential energy or stored energy into kinetic energy of motion. What word describes Newton's first law that says an object is the projectile will stay at rest unless acted upon by an unbalanced force? Well, objects continue to do what they're doing because of inertia. So if it's staying still, it wants to stay still. If it's moving, it wants to keep moving, and that is due to inertia. The formula of force equals mass times acceleration can be used with catapults to determine the force applied to the projectile by finding the projectile's mass and acceleration. Which of these Newton's laws describes that? Well, when we talk about how different masses and accelerations affect the force, that is always Newton's second law, or force equals mass times acceleration. Newton's second law. We pull back the arm and we'll launch it forward. It goes forward and it launches. It goes. We pull it back so it launches forward. Equal and opposite. This represents Newton's third law. So as we pull back the arm, it pushes back on us. The spoon goes forward. The projectile pushes back on the spoon. When it hits the end and the spoon stops, then the inertia of the projectile takes over and it continues to move in a straight line at a constant speed. And then gravity and air resistance take over and slow it down. It's because friction slows everything down. And last one, how hard it is to stop. So if I launch something, how hard it is to stop that object can be calculated by multiplying mass times velocity in the equation P equals m times v. Although it doesn't start with a P, what property are we talking about? We are talking about momentum. Momentum is a measure of the mass and velocity, or basically how hard it is to stop a moving object. Make sure you submit. The last slide, if you wanted to, and if you didn't create one, that's fine. It's completely optional, as all projects will be, because I can't really enforce it. If you made one and you want to include a picture, you're welcome to. This is mine, or one of mine. If you didn't make one, you don't need to write anything down. But if you did make one, I'd love to see an example one that people have made. I'd love to be. I'm not the only person who actually did this. When you're done, again, when you see the tab to start over on an Nearpod, that does not mean you have to go all the way back to the beginning and do it again. That means you are done. I will be grading this assignment, so please make sure that you are completing it. Hope this video key helps a little bit. If you have questions, you can always see me during study hall for any additional information. All right. Have a good rest of your day.